Welcome back to the lab. Today we're going to talk about a few different power supply topologies that were considered for the proof of concept platform. H-bridge, flyback, and buck switch mode power supplies. While considering these topologies for our proof of concept platform, it was important to keep in mind that we should pick a topology that is most similar to the system we eventually want to create. This seems simple, but why? To my knowledge, the control system will be fairly similar across the board. The components required for each topology will be approximately equal in value for a similar output power and similar ripple. But the reason why I'm using this architecture, the architecture that's most electrically similar to the final implementation, is because it will allow us to expose more minor glitches and headaches that we might not notice in simulation land. Physics is unforgiving, and missing minor details can result in the real performance of a part to be drastically different from the ideal performance. Kind of a side note, but I, personally, don't enjoy being electrocuted. I don't judge what you do in your home, but it's just not for me. High voltages and large currents are no joke. They can really hurt people. Now that's why our test platform will be designed to use lower voltages for when we need to get up and close and personal with the circuits. If you don't believe me that high power circuits can get scary, check out a phenomenon called arc flash. Speaking of explosions that are made of molten and vaporized metal, every switch mode power supply topology has a slight difference from the others, and the little quirks of each topology can cause some headaches. Higher power implementations naturally come along with some headaches on their own, but we'll talk about that in a future video. Since I know what the final implementation of this design will be, unless of course our proof of concept testing suggests it won't work as well as we need it to, I think it's important that we explore the quirks as soon as practical. I know what is typically done for this topology of power supply, but I also want to confirm my experience and research with some measurable results before relying on it. This process will give us a chance to fix any small errors in the design or flaws exposed in the part selection before we crank the power up to 11. For the proof of concept test platform, I considered a few different topologies. Let's walk through them now. The buck converter is a classic. It allows for stepping down a higher voltage to a lower voltage. It operates by allowing current to flow when the switch is closed, and then the current will build up in the inductor at a rate proportional to the difference in voltage across the inductor. This current is shared between the load and the output capacitance. When the switch is opened, the current is pulled through the rectifying diode and continues to supply the load. If voltage regulation is established, the nominal output voltage is the center of an approximately triangular waveform due to the capacitance charging and discharging through the different parts of the switching cycle. The output must be less than the input voltage, and the maximum output voltage is dictated by the output current required and the losses across the inductor and switching element. The buck topology is not isolated and allows for voltage regulation by tapping off of the output of the converter and then feeding that back into the control system. A flyback converter was also considered for this test platform. This topology is the only one that requires a transformer, or rather coupled inductors, to function correctly. It operates by letting current build in the primary inductor when the switch is closed. When the switch is opened, that current comes out equal in magnitude of the coupled inductor with an opposite sign. Then that goes through the rectifying diode and into the load/output capacitance. The output voltage can be greater than, less than, or equal to the input voltage. This topology can be isolated, depending on how feedback is implemented, and this topology allows for voltage regulation by measuring the feedback voltage on a second primary side winding, or by measuring the voltage directly on the secondary side of the coupled inductor. I'm calling this a coupled inductor instead of a transformer due to a matter of pure semantics that is so completely irrelevant to this conversation, I can't even start. If you'd like to go down a tangent for 20 minutes, let me know in the comments. The last topology that we considered is the filtered half H-bridge topology. This topology is like a buck in the sense that an inductor is used to filter out the switching frequencies to create DC, and the output voltage must be less than or equal to the input voltage, but it's also very different. It operates by switching between VCC and ground on one side of the inductor, and it allows the average current to pass through the inductor. The output capacitance averages the current being passed through the inductor, and the current deltas turn into small voltage deltas, and that's proportional to the capacitance, yada yada yada. This results in a significantly smoothed version of the hard switching on the other side of the inductor. I like to think of this as a big power low-pass filter. The filter doesn't need to have great performance either, since we really only want to pass DC, which ideally has a frequency of 0 Hz and in practice is very, very close. Everything above that should be filtered out. The H-bridge topology allows for voltage regulation through direct measurement of the output voltage, which isn't a big deal since the output can't be isolated from the input since it's being hard switched with FETs. The great thing about creating something like Project Darwin is that the circuit will be communicating with us through voltage, current, ripple, step response, settling time. These all tell us something important. As we make changes to the control system, or the load, these parameters will change. The way that they change will help us to understand how much margin the stability of our control loop has. For a brief overview of stability, stay tuned! We'll be talking about stability very soon. When faced with the task of choosing between these topologies, there are those that I'm more familiar with, those that I think would be easiest to control with a microcontroller, but ultimately I needed to pick the one that was most similar to the system we are supposed to be prototyping for. If you don't know why it's important to have your prototype be similar in topology to your final implementation, check out part 1 of the Project Darwin series where we mention both the point and value of a proof of concept phase. In this case, the most similar topology is the filtered H-bridge. There's a lot that can go wrong when implementing a filtered H-bridge. There's even a lot that can go wrong with implementing the digital control system on a microcontroller. One of the ways that this could all blow up is if the sampling period is not the same with regard to what the control system expects. This error can be compensated for, but that can get messy, and by messy, I mean really computationally expensive. Since we're going to use the ARM-based PID loop library, I'm not sure whether this is built to compensate for errors in the sampling period by default. And besides, the ARM M0 processors we're working with, they're not particularly powerful to start, so we're better off making sure that the hardware can achieve a constant sampling period to make our life a lot easier. But we need to make sure we can do it. Continuous time filters implemented in hardware are conceptually simpler, well, at least to me, than discrete time filters. But they tend to be less configurable after the board is built, since they're made of op-amps, and they're typically limited to lower order filters, since they're made of op-amps. With a digital system, the only limitation to the order of the filter is the processing power of your processor. Adding additional layers to the control loop or implementing different operating modes, higher Q, optimizing for lighter heavy load, all of that's really easy to do on the micro. We'll be able to dynamically change the response of the PID loops based on load level, if we would ever want or need to. I'm hoping to find one set of coefficients that meets our specs across the board, regardless of the load, because having discontinuities in my control system makes me cringe, but I fear that the ripple might just be too large in the no load condition if we optimize the control loop for the full load condition. Speaking of that full load condition, filtered half H-bridge topologies have one pretty big fundamental quirk. If the timing of switching the high side and low side FETs isn't just perfect with guaranteed dead time, we'll short the input voltage rail to ground for a brief moment, causing the MOSFETs to meet an untimely end due to excessive currents. So that isn't ideal. Making matters worse, they're most efficient when that dead time, or the time when neither switch is on, is kept to a minimum. So because we want to push our converter as close to that point where it'll rapidly destroy itself by shorting VCC to ground, we need to make sure that we're testing the control system and output stage when we're using a supply that has a programmable current limit, at least from the start. That'll give us a chance to find, diagnose, and mitigate some design defects before the electronics are damaged from large stresses that would have otherwise occurred without a current limit. With that programmable current limit in place from a lab power supply, shoot-through won't cause an explosion or parts flying off the board, it'll just cause some heat to build up in the heat sinks. Due to the large powers at play in the final design, we can't really use fuses to prevent circuit destruction. That's why it's important to test it now in the proof of concept phase. Sure, we'll have a fuse from the main power input, but a fuse that allows 1 kilowatt through it won't do anything to prevent our MOSFETs from being destroyed if they experience shoot-through. We need to be careful to prevent noise from the power input, ESD, and radiated electromagnetic energy from coupling onto the gate drive signals such that it could cause shoot-through. There are a lot of ways that shoot-through can occur, and we need this supply to operate 24/7, 365, or at least as close as we can get. We'll need to be careful to ensure that our system is hardened against electromagnetic radiation and conducted emissions from nearby equipment, just to name a few. These are just a handful of the many challenges this project will face, and a handful of the reasons why it will take so long to execute correctly. Well, there you are. We've selected the filtered half-H bridge topology for our power supply output stage of our control loop test platform. This is all for Project Darwin. We made this choice because it's very electrically similar to the final topology we want to implement, and it isn't significantly more complex to drive than the other switch mode power supplies topologies. It'll incorporate voltage and current monitoring in the appropriate locations, and it'll allow us to achieve about 90% of the functionality required for our final voltage regulator stage. Once we get the control loops dialed in, we'll turn up the input voltage and make sure the switching circuits can handle the larger voltages at play. Stay tuned for our future videos, where we'll determine whether it will be better to build or buy this test platform and start exploring the STM32 microcontroller HAL ecosystem, and totally, not at all, get super frustrated with it at all. It's going to be great. I love software. I think that selecting a proof of concept switch mode power supply topology is a big step forward. If you think so too, or if you think that H-bridges are cool, let me know by hitting the like button on this video, subscribing to the channel, and leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EE for Everyone, and thanks for staying till the end. Bye!